If you can remember yesterday, actually, we covered an introduction about power electronics, right? In that lecture, if you can remember, what type of converters we discussed, just as introduction?
DC to AC.
Yes, exactly. So let's revise those. We have different types of converters. The first one we can see AC to DC, and then DC to DC, DC to AC, and also you can
AC to AC.
AC to AC. So this is converters. The first one called rectifier again, and this one can call it choppers. This one DC to AC inverters, and this one AC to AC converters, or you can call it regulators. Or converters. So this is the basics where application of power electronics can be found. Now, if we look at those, we are using switches, right? So switches like diode and transistors, thyristors. But if we're trying to classify those ones, actually it is classified into three types, which is based on the control type. The first one is uncontrolled, two types of switches, power electronic switches are uncontrolled, which is an example of this one is the diode. Controlled or half controlled or semi-controlled, let's see. Semi-controlled like thyristor, and we will discuss the difference between them. And the last one, you can see fully controlled like transistors or GTOs in terms of thyristors. So this is the main three classification. Today we will talk about the rectifier, and we will tackle those two in the rectifiers. So we will see the rectifiers AC to DC, and we will try to tackle those, and we will see the difference between them. So if we go to the diode, if you can remember, do you remember the characteristics of diode to those who studied in electrical or who take basic courses in electrical department?
To allow the current to move in one direction.
Yes, exactly. So, do you remember the IV characteristics of that one? Can you remember? Looks like this. And then like that. And here is the voltage, and here's the current. Right. And actually, the diode turn on when it's in. So here you can divide those into three areas. The first area, which is this one, which is forward biased. So this area here, you can call it forward biased, where the diode conducts, biased, and here reversed, biased one, and the last one is the breakdown, where the diode may break down areas. Actually, when power electronics, actually, the diode recommended to work in these two areas. This one sometimes could be destructive until it is specified by the manufacturer of those diodes. So those areas where we are working. So in forward biased and reverse biased. And let me show you how it will work in both like those. So let me assume for the first time, if I give you a circuit like this, a DC source, okay, and connected to a diode like this one and to a resistance like this one. Okay. If we look at that one, this is the DC, right? And the polarity, this is negative, this is positive, right? If I'm looking to that one through that node here, this one exactly the same as that one, right? So what do you think? Which, if I call this one, this point or the terminal of this place of this diode, this is the anode and this is the cathode. In this case, the voltage, in which point is higher, in the anode or in the cathode? In the anode. So if the voltage here is higher because the voltage here it's higher and then at the same node, so this is VA is higher than VK, right? So definitely VA higher than VK, therefore the diode will conduct. So in this case the diode will conduct, and it is on this operation region. Okay, so it is in forward bias, so the diode conduct. But if I'm trying to look at that one where the diode here in this area, I can assume the circuit, I have a circuit like this, for example. Let's put that one, let's say both is positive, negative, and reverse that one to this side. And let me call this one the same thing. This is the cathode, and this is the anode. Which is higher? The cathode, definitely. It has higher potential voltage. Therefore, it will not conduct. You see that if the voltage here is higher, like that case, it will conduct. The voltage here is higher and the diode is reversed, so it will not conduct. So diode is just conduct in one direction and then it stops the current to conduct in the other side. Did you get it? So it conducts in one direction only. So this is an example. Now, if I apply this one to an AC source, instead of DC like this, if I make it in an AC source alternate like that one, and then if I connect the diode like this one, and then connect the circuit like this. So this is my circuit. An AC source. How the AC source operate? Sinusoidal. We can say it's sinusoidal by default if we are looking to our system, but it can be also square wave if just in the lab if we like to test it, or even triangle wave. But for the practically with the distribution system, it is AC exactly sinusoidal one. So if I return back to this circuit here and plot it again. Okay, so I will have this diode, and this is the resistance, and like this one. Now, if I'm looking to this one it's AC, it alternates like this. So this voltage here, it's in AC like this. Right? So it has positive side and negative side in terms of voltage. And I can assume that the cycle is 2 pi, so this is pi, and so on. So this is 3 pi, and this is 4 pi. So if you assume that if you assume that like our system is 50 hertz, for example, the frequency, that means the pi is 0.01 second, right? Which is 1 over. So if you have the frequency 50 hertz and you want to get the period is 1 over 50, right? Which is equal to 0.02. So that means here this is 1 period, so it will be 0.02 seconds, right? If you would like to convert it in time. Now, if we look at that one, again, this one, this side, from here to here, the source is positive, right? Positive. And from pi to till 2 pi, it's negative, right? So if I'm looking to this, that means during the, if I apply this one here to that, to this interval and that interval, I can draw my circuit like this. This is positive, and this is negative, and then this is my source. So my load. So in this case, this is positive from here to here, until this interval here. From 0 to pi. From 0 to pi. On that interval, this is the polarity of my source. In this case, this one, in which region on that characteristics, if you can repeat back to that one, can you tell me which one is on that one? Like this case, right? It's in forward bias, right? So that means it will conduct, right? So if this one will conduct, and I would like to measure the voltage, across that one, across the load, here. This one conducts, right? So if I assume just an ideal diode, if I assume that an ideal diode, that means when it conducts, the voltage is 0, right? But in practically, it could be 0.7, and sometimes for the power applications, you can find diode with a voltage drop between 0.2 to 2 volts depending on the manufacturer. Is it clear? So now that means if I assume it now 0 drop across this one, that means it is in forward bias, so this one will conduct, so 0 voltage here. Can you tell me what's the voltage here? According to the KVL, it's same as the source one, right? So if I have here that, this half cycle, I will get in the output here the same, right? The same with the same peak, because I'm assuming that there is no voltage drop across that one. So this is from 0 to pi. And after that, in the second half cycle, from here to here, I mean from pi to 2 pi, is the source negative or positive? Negative. So when it is negative, that means it is located in the second region, which is reversed biased. Therefore, it will not conduct. So that means in this case, I will have the circuit like so. This is negative and this is positive from here to here, and this circuit here. So this diode will not conduct because it's in reverse biased. I can see this one is higher than that one, which is the cathode is higher than the anode. Okay, so it will not conduct. Therefore, the voltage across this one is equal 0. Therefore, during the second period, from this time, I can assume it like this one will be 0, right? So now, this one, it will be repeated for the next cycle and then so on. So I will get like this, and so on. So That means, do in this output now, output voltage here, do we have negative part? No, right? We don't have negative part. That means I converted my input from two polarity cycles to one polarite, right? Which is the positive one. Therefore, that means I have a DC output, right? But in this case, the output is not pure DC. It has some harmonics components and need later a filter to filter those. But now I can get those output as a DC voltage. I would like to show you this one by simulation, and then we will move to the full wave rectifier. So if you allow me, I will show it to you by VSIM. By the way, you can download the VSIM demo from the online. So this is VSIM. This is the main sheet of VSIM. And you have here, this is different types of sources and load and whatever, or you can get it from the elements here. So either you can have them from there, or you can have them from down. So for example, if I need an AC source, this is my AC source, right? So this is sinusoidal source, okay? And then if I need the diode, for example, this is my diode, right? And then if I need a resistance, this is my resistance, which is the load, or the resistor, sorry. So now let's connect those by wires like that one, and then from this terminal to that terminal, and then again to this terminal like that, which is simple and easy to implement. Now you can put, for example, the value of the voltages which you would like to. So open this one, and then on this window here, which is the sine one, you can add, you can name the source. For example, you can call it VS, V source, whatever you like. And then the value of the voltage in peak, for example, if I assume this one, what's the value of this voltage source? 240, right? So what is the peak of 240? This is an RMS, right? So the peak is 240 multiplied by square root of 2, which is equal 340, right? And the frequency is 50 Hertz. So now I can test this one if you would like to see this source, this is a voltage probe, or you can assume it like a voltmeter. So if I put it here and then connect it like this, I can see the output waveform of that one. So just add that control. This is the control time. But just to here only just to define how many cycles I need to run. So this is the time domain. For example, here I can see that this is one cycle, right? And the time 0.02450 Hertz, right? So if I need 2 cycles from here to here, that means I need 0.04 seconds. So I will select 0.04 seconds. So the total time 0.04 seconds, and the step, which is the incremental. So that means start to simulate incrementally increment by 1 times 10 to minus 5. Then close that one in order to select that one. So now if we run that one, we can see the source. See, this is our source. So the source is sinusoidal, 40 milliseconds, which is 0.04 seconds, right? So this is our input. Now, if I go to the other side, which is this side, where the load is located, and then I bring another voltmeter to measure the voltage across the load. So let's see that. And we can name that output. So we can put, for example, V out, okay, and then let's run that one. So if we run those, now run that one, let me close this one. So run both. I can select which one I need. Shall I would like to block, for example, V out or the source? For example, if I would like to block V out, I can block it. I can block both. This is V in and this is V out. See here. The V out, this is the V in, and this is V out. You can see on that curve here, the blue one is V out, and the inner one, which is here, the red one, is the output. So we can get that DC. So now, that means by using the diode, I converted the AC source to DC. The only difference that until now I can see that it's not pure DC, it has some ripples, or you can call it harmonics component, and then later on it can be improved, or it can be filtered by such filters to decrease those ripples. So this is the first circuit, which is the basic circuit, which is known as half-wave rectifier. Practically, the efficiency of this one is too low if we compare it to the full-wave rectifier. Full-wave rectifier, it uses 4 diodes instead of one diode. So 4 diodes in order to utilize the second half cycle as well. So instead of losing that one, I will utilize this one. How I can do, instead of just using one diode like this, I will use 4 diodes. So let me go through that first, and let's discuss it. So if I look at the 4 diodes circuit, so this is the 4 diode, and you can connect them all together like this by wires to make a bridge. An example of this one, you can see that one here. This is a 4 diode one. Okay. So if you look at this one, you have 1, 2, 3, 4 diodes, and the input to the AC is this side, and the output is that side. So you can have it up that one, you can let it through. And if you look at inside that one, this is just made for the lab, but this is the, if you can see, this is the module or the chip, that it has 4 diodes inside that one. Now, so this one, it has 2 input terminals, this one and from this leg as well. So 2 wires for the input, and also there is 2 another terminals for the output on that bridge. So the AC should be located or placed here, which is the input, and I'm waiting for the output from here, which is the DC. So the load should be connected to this side. Is it clear, Shalal? So that means if I have an AC, the same thing like this, okay, and I can assume it now 240 RMS, which is like this system. So the peak of that one, so the peak of this one is 340 volts, because it's an RMS, right? So, and the frequency is 50 hertz, like our system. And then 4 diodes, and then connect this one to a load, a resistance, or a resistor for the first one. Okay. So let's look at that one. The same thing we can analyze like before, but now we will gain that this part will be inverted to the other side. That means we will utilize the whole wave instead of just the half wave. Okay. So if we look at to that one, this is my, I can plot this input voltage, which is, you can plot it on this, and you can continue for the next cycle. So this is one cycle, this is the voltage, and this is 0, 2 by, 2 by, 3 by, and you can continue so on. So for, in the period between 0 and pi, okay, in the period between 0 and pi, definitely this one is, let me take another color. In the first period, this one is positive, right? And this is negative, right? So that means I can say this is higher than this one, right? Right? So this is the same node, right? And that went to the other side, which is that node, right? So, and the same thing, this one here, this one here, this is to the negative, right? So definitely this one is higher, right? So this is the negative, and this is the positive, right? And the same thing here, you look at to that one here, this is the positive, and this one the negative, right? And that one, both the positive one and the negative one according to this sign and sign, right? So if you look at to that one now, the anode here is higher than the cathode on this diode for the first half cycle. I'm talking between this period to this period, from this interval, from 0 to pi, okay? Between this point and this point. Okay. This one, is it in forward bias, right? So this one will conduct. Conduct, right? What about this one? No.
It's not good.
What about this one?
No, no,
No. What about this one?
yes.
Yes, it will conduct. So if I just trace my current now, so I can see that this is the negative and the positive. So I will go through the current. So this one will conduct, right? So the current will go through this one, but it will not go to this side because the current cannot go to the reverse side like this. Okay? So the current will go through this one. When it reaches this place, there is two paths, right? But this one blocked because of the diode. Right? So the current will continue toward this side and then through the node, and then when it reach here, there is two paths, right? But this one it's blocked. So it will continue on this side and return back to the source like this. So now, if I dot that one, I will see that I can call this one D1, D2, D3, and D4. So D1 and D3 are conducting, right? So in this period, D1 and D3 conducting. So if I block that circuit, which is this internal one, so this is the first diode, which is that path, and then to the resistance, and then come back through this diode toward the source. So this is my circuit, right? So again, if I assume that diode is ideal, that means that the voltage here is 0 volt, right? And here, 0 volt, right? If I assume it ideal. Is it correct? So what is the voltage across that load?
So
Exactly, with the source, right? So definitely I will get this voltage, which is, I can dot it with the black one, so inside that one. So this is my output until here. So this is, the black one is V out, and the current passes through this loop. Now, in the second half cycle from pi to 2 pi, now let me take the blue color. Now, the voltage, which is the source voltage, is in the negative side, right? So I can assume this is the opposite, right? Correct? Now, definitely here it will be positive, negative, positive, negative, positive, okay? And that one, if you look at this one here, this is positive, and this is negative, and for this one here, this is negative, and this is positive, correct? So that means in the second, this one will conduct, which is D2, see here, this one positive and negative, right? So this is the direction. Remember the direction of the current in the diode to this direction. So it conduct only in one direction like that. It doesn't conduct in the opposite direction. So that means this one will conduct and will turn off because it's in forward bias. So it will allow the current to pass through this diode, and it will come back through this diode. So it will not conduct on that one. So D in the second half cycle, D2 and D4 will conduct, right? Again, if I dot the circuit, if I'm trying to trace, that means the current in this, it will start from here, it will go through that wire. When it reaches to this point, remember the current will not go to the opposite, so it will go up toward this diode, and then when it reaches point, it will not go to this direction because blocked by this diode, so it will continue toward the resistance like this. Okay. When it reaches to here, this one, it will not conduct because this potential is higher than that one. It's in reverse bias, so it will, the current will go to this one, to this diode, which is D4, and go through this wire and come back to the source like as a loop. So this is the second loop. So we can plot this one. So the current in this case, and the second one, it go through D2 and then toward the resistance, and then through D4, right? So again, what's the voltage across that one? See that loop? The voltage in both loops, the current is entering from this side, right? So both of them in the same polarity, in both half cycles. So what is the voltage across that one during the second half cycle? Positive. So that means it is equal the source. Therefore, in the second half cycle, the output across that resistance, we will get that envelope up from the opposite of this one. Okay, so I can get, this is the output. So this means if we continue in the next cycle, so we'll get this output, which is a DC, only it's in one polarity, right, the positive side. Is it clear, Shabab? That means I converted the AC to DC. If we are looking to this reverse, it should definitely, it will be this reverse. We can later talk about this after the lecture if you would like to discuss that one.
Can use capacitors.
Yes, to filter those. Exactly.
Sir, does the diode affect by the frequency?
There's different types of diode. It could be line diode, it could be high frequency diode, it could be Schottky diode. So it depends what you need. For our cases, this is like a line diode. So yes, it is affected by the frequency and affected by even by the which is known as the reverse, which is known as the reverse of that current.
Do you use power diodes here?
Hmm?
Is it power diodes?
Power diodes, exactly. So let me simulate that one. Let me show you an example of this. So let's go to that. So 4 diodes. Okay, this is the 4 diodes, right? And just bring AC source, connect it to this side, and then to that side, and then a resistance. Okay, and then can add the values. For example, you can put this one as 340 as we discussed here, and then 50 here, and then add the time. We need 2 cycles, 0.04 seconds, like the previous example. I'm doing the same thing like the previous example to show you the difference. Okay. Now let's add a voltage probe in this side, which is for the VN dot VM, and another voltage probe to the other side for the load to measure the voltage across the load. So look at the output. It just rectified. Now I have, instead of AC, I'm having DC. The only difference that I have some ribbons on this one. Okay, and then later on we can reduce those ribbons by adding a capacitor, like what we said. So this is the output. So if you would like to compare between this and the previous one, this one, it hasn't been utilized for the half-wave rectifier. Now the value of the voltage is higher for this one. Is it okay, Shabab? Is it clear? So now let's go to the slides. In the slide, I'm using the second. If you remember that when we discussed that one, we said that there is uncontrolled, like the diode cannot be controlled actually when the voltage in forward bias will conduct. But thyristors, for higher application, it can be controlled and it can be used for the drive applications. The thyristor operates approximately like, you can see, like diode, but it has a little bit different characteristics. We can discuss it later, but I can tell you that it works the same thing when it is in forward biased now, and the only difference that you need to send a current signal to turn it on. Without these conditions, you cannot turn it on. So that means it have control. You can, for example, if this is the thyristor, if I give you an example of this one, with the thyristor, the same thing, has half-wave rectifier, but instead of the diode, I'm using thyristors and connected to a resistance like this. Okay, now this thyristor will not turn on just because it's in forward bias like the diode. You need to send a current signal to this gate in order to turn it on. So this is the difference between them. So this one requires the signal. For example, if you have the input like this is the input signal, which is here, and okay, I need also to send a signal with this one. So for example, if I assume my signal, I sent a signal using microcontroller with a drive circuit, and I sent the signal at this point. And actually, you don't need, once it's in forward biased, you don't need to keep the signal on. Just send it as a pulse, and then once it turns on, that's enough. And it will keep on until the current goes to 0. Okay? So that means, with the case of resistor, it will turn off at this point. Okay? Like the diode. So if I send the signal here, and even if I send a signal here, and then the same signal here, the same point. Okay? If I'm looking to this one, this is, let's assume this is 0, this is pi, and this is 2 pi, like that one, and so on. If I'm looking between 0 and this point, for example, which is known as the firing angle, you can call it alpha, between 0 and alpha. Okay? This thyristor is in forward biased. Okay? But it will not conduct. It will not conduct, waiting for the signal. Once the signal reach the gate, it will turn on. So the signal normally, practically, it should be higher than the latching current, which is the current that enough to turn on the circuit all the time. So now, if I'm trying to block that one here, definitely this thyristor will not conduct. Therefore, the voltage across this load is 0, right? So I will not get output voltage during that time between 0 and alpha, up to here. And then after that, now the diode is still in the forward bias, right? The thyristor is still in forward bias, right? But I send the current signal, which is this one. So the thyristor will turn on. So if the thyristor here turn on, that means it's conduct. So what's the voltage between this and this? Same. So I will get the voltage. So the voltage will be the same from here to here. So the voltage will jump like this, and then will continue until the current goes to 0 across the thyristor, or sometimes called the current less than the holding current, practically.
So when we send the signal, we don't have to continue sending the signal.
No,
Only
no,
to
no.
turn it on
Exactly.
until the voltage reaches 0.
Yes, or reach approximately, practically, it should be less than the holding current, not exactly 0, a little bit above the 0. Okay. And then it will stay 0 for the next, waiting for the next signal. Now, the second signal sent at this point, but my question, is the thyristor in forward biased in this case? No, right? It's in the reverse because the voltage is in the cathode is higher than the anode, so it will not conduct, right? So it will not conduct, so it will stay 0 and 0. When it reaches this point again, this thyristor now in the second mode, which is forward biased, but there is no signal, right? So again, it will not conduct until here. Therefore, it will turn on that point. And if you can see, what's the output now? Still it's a DC, right? But now, if I compare it with the previous one with the diode, that means I send the alpha after a while, which is phase shift. That one makes the output voltage, the average output of this one is less than the previous one. So I can control my output voltage using the firing angle. So if I increase the firing angle, that means I'm decreasing the voltage, right? So if I apply this one, for example, a DC machine, I can control the terminal voltage, so I can control the speed of the DC motor, right?
I think it can be used also for AC motors, to control the speed of AC motors.
No, because the output now is DC.
No, I mean the thyristor. You can use it. It's
Yes.
a part of the driver to control the
Yes,
AC motor.
you can use the thyristor to control the AC, but not like a rectifier, like a regulator. You can put it back to back thyristors, and you can control the AC output. Exactly. Any question? Sure. Do you have any comment or anything? So let's also simulate those and let's see the output. So I will change this one directly to a thyristor, and for the other one, also for the other circuit, I will change it to a thyristor instead of diode. So thyristor, this is the thyristor, right? And I can add a gating signal, so I can select the time of that gating signal. Practically, you can implement this one either by analog circuit or digital circuit. This is up to you and the design. Or even you can buy driver circuit and then with the microcontroller, and you can use it to control that thyristor. So here in the simulation, I will use that signal generator. So I will turn it on, and then it should be 50 Hertz because I'm using 50 Hertz. And then I will send the alpha, for example, after 45 degrees. So that means this is 0, and this is 180, right? So I will send, for example, my signal here at, assuming that when it's 45 degrees, so I will send that signal at 45. 45 degree, and then I can keep it now just for the simulation, just 45 degrees, so it will be until 50. And then let's also see that one. Okay, so I call this one current signal or safe. Okay, which is signal. So now let's simulate that one. Let's see the output. See the output, or we can block the whole thing in one. Let's run it again and then block the input, and then in another here, another window, let's block the signal, and then let's block the output and the others. You see? See that this is the input signal, which is here, and then I'm sending this signal to that gate here at this time, which is at 45. So at 45 exactly, while this thyristor in forward bias to turn on. Okay, so it turn on. Therefore, the voltage is reflected here, and you can see that voltage, which is exactly between 0 and pi, is that one is again appear here, and then in this mode here it is 0. I did not send any signal, and then the second signal it should be here. I can send a signal here and it will not appear. I can add that signal if you want, and you will see that it will not appear. So if I would like to add a signal, I can make like 45. You can make it like 100 Hertz, or sorry, 2 volts. Let's add 4 volts. Run that one. Sorry, this is plus 2, right? 2, 10. So if I add 4 volts, that means I need to add another signal, which is 180 plus 45, right? And then another one, which is 180 plus 50, right? In order to send the signal at that second half cycle, right? So if I add those, let's add that, run those. Oh, there's a mistake. Oh. You see, I sent a signal at this time, but the thyristor in the reverse bias, so still it is not contacting, right? Did you get it? Now if we go to the other one, which is full wave rectifier, I can discuss it directly in the simulation here. Sorry. This one. So let's add thyristors. If you can remember from the diode circuit, okay, that this diode, which is this one, operate with this one, right? And this one operate with this one. So we can use one gate, one signal. We can use for the whole thing, for the whole of those diodes, just one gate, all of them the gating signal, and then definitely this one, if this one in forward bias and this one in forward bias, it will conduct, right? For the first half cycle, صح? Right? And for the second half cycle, this one or this diode and this diode will conduct, right? So if I make a signal generator now and then add, add the gating signal to this one and then to that one and then to this thyristor and one to that thyristor, which is here. Now I'm sending those signals, and let's make it 50 Hertz, and let's make it like the previous one, 4, right? And I need it at 45, and the second one at 50, which is one signal, right? And the second it's 180 plus 45, right? In the second half cycle. And should be end at 180 plus 50, and then that's it. Right, so this is the 4 points, 1, 2, 3, 4, right? So close that one, and then let's take this is, let's call this one signal. And then this is my input and this is my output. Let's take this, that's it. Now it's ready to simulate, right? So let's simulate it. Close that one first, and then run the simulation. So Vin, this is Vin, right? And this is V, the signal or the current signal. So I'm sending. Is it okay, Shabab? And let's see the output now. Is it clear? So that means I can control my output, right? As a DC. So now if you look at for the previous one with diode, it was completely full, right? So that means the average voltage is higher. Now I started to decrease the voltage by controlling the firing angle, which is alpha, right? So let's discuss that one. Between this period till here, this is positive, right? So therefore, this diode and this diode are in forward biased, right? So, but there is no signal, they will not conduct. After that, after this time, which is after the firing angle, which is 45, still diode 1 and diode 3 are in forward biased, but now because the signal are there, so both of them conduct, right? Once it conduct, they operate like what we have seen in the diode rectifier. And if we, in the second half cycle, the same thing. In the second part, which is that one, when I send this signal, okay, that signal which is in the arrow there, this one, at that time, this diode which is here, D2 and D4 are in forward biased, okay? Therefore, they conduct. And we got this output voltage like that, and so on. Now, if you would like, for example, to see this one, to operate the thyristor like a diode, put the firing angle equal alpha equal 0, exactly. If you put alpha equal 0, that means it will operate like a diode with higher average voltage. If you look at to the average voltage, you can measure it from here. The average voltage, which is the average of the V out now, it's 18.4, sorry, which is 184 volts, right? If you change this one, to 0, the phase shift, you send this one at 0. Let's add all this. So 0, and then I will keep it for 5 degree, okay, on. And then for the second signal, 180 plus 5, sorry, 180, okay, and then at 185, right? So this is the 2 signals. If I run those, You see, it's operate like a diode. Okay. If you look at to the average voltage of this one now, you will see that V out now it's higher, 216, right? Let's go now through the slide. Now you understand it, right? You understand both. Okay, let's go through the slides. So that means if you would like to use diode, you can, for the slides, I'm just covering the thyristor. The thyristor is general one. So the diode, you can assume it like one case when alpha equal 0. So I will cover that. So let's start. Power electronics converter is the term that is used to refer to the power electronics that convert or control the voltage we discussed yesterday in order to meet the required load specification. These converters can be classified as rectifiers, choppers, AC to AC converters, and DC to AC inverters. And then we will cover rectifier for today. Rectifier can be classified in the term of it is uncontrolled rectifiers like diode, fully controlled rectifiers like thyristors, and they can also sorry about that, silicon, so fully controlled rectifiers are built in with silicon, which is like thyristors. This is the diode. So just can change it to it's semi-controlled, and then fully controlled with the thyristors. So this is the half-wave rectifier. You have the input, and then if you apply a firing angle at a specific time like this one, the output you can see it's between alpha and beta, in this case beta where the current flows or the current goes to beyond the holding current at this point, which is where the thyristor will turn off, right? So we will get that output voltage. And this is how we can put it by math. If I have two-step function and then subtract those, that means I'm creating signal, right? So this one, between here, both alpha minus alpha beta, 0, right? 0 minus 0, 0, right? And between alpha and beta, alpha is 1 and u beta is 0. So 1 minus 0 equal 1. And after that, you subtract this one, both of them 1 minus 1, 0. That means I created a pulse like this mathematically, right? So you can create the pulse like that one. And you can control the period or the time of on and off. So in this case, I will get that Vs multiplied by that one. I will get IR at the value of that voltage when it is on period from here alpha to beta, from this one to that one. So this is the output, and this is the current. The current, if you would like to calculate the current, it's the ratio, right? Because it's a resistive. So you divide just V over R, right? You will get the current. And how we calculate average actually? Average, you will take, like we did an example yesterday, an example when we calculated one square wave, right? The same thing here. What is our period in this case? That our period from here till here, right? 2 pi. So 1 over 2 pi, okay? And from 0 to 2 pi, VSU. And if you look at this function here, the on from alpha only to pi, which is beta, right? From alpha to pi, and then what is the function inside that from here to here? Exactly same as the input voltage, right? So equal Vs, and Vs in this case it is V maximum sine omega t, right? So if you substitute this and then integrate, you can reach to this equation. So V average, which is the DC output from this half wave rectifier equal B max over 2 by multiplied 1 plus cosine alpha. So in case of diode, if I would like to get the average, what will be? It will be 1 plus cosine 0, which is 1, so it will be 2, and it will cancel with this 2. I will get V max over pi. Exactly. And for the average current, V average over the resistance as a ratio, which is that one divided by the value of this resistance here. And if you start to change the firing angle, that means you can get different, but like it shows this is the relation, right? As you increase alpha, the average output decreases, right? The maximum at alpha equal 0 and then decrease until you reach 0 at pi. If you apply that equation, right? So that means good to control that for the drive control. You can calculate the RMS values if you would like, the same thing. This is the V average, and then you can get the RMS by squaring the function and divide it by pi and then put it under square root. So you can see root, which is this root, mean is the mean of the function where the operation is, and the mean of that square, right? So this is how we can translate it. Okay, we can, example, if we'd like to have an example about that one. Example, if you have an AC like this, and you would like to get the RMS, the first thing, I will show it to you analytically, okay? What you will do, the first one you can start with the square. Square this function. If I square this part, that means I will get a signal like this, right? Right? And then if I square that one, I will have this, right? And then if I square that part, I will get that. Now, if I try to get the average of this one, definitely I can get that average, right? And then if I put this one, this average under that square root, I will get this value, which is the RMS value, which normally we use it in our calculation in the AC. Okay, this is how we can get those. So the RMS also it can be obtained from that output value, and you can use that integration, and then you will arrive to this equation. The RMS of the half-wave rectifier equal V max over 2, 1 minus alpha over pi, sine 12 over 2 pi. And then the voltage also, you can see that the RMS decrease as you increase the alpha. For the full wave rectifier, we discussed it now while the simulation, the same thing. It operates into two modes. The first mode for when the half cycle is positive, you can assume it to this side. So this one and this S1 and S2 will operate. Okay, but you should send a signal right before sending any signal. Both of them will not work. And then for the second half cycle, you can assume S3 and S4 will turn on, so they will conduct in the second half cycle. And then the direction, both currents from the first half cycle and the second half cycle are in the same direction. That means I got the same polarity across the load. That means I'm having a DC output, right? So this is the output which we simulated. Now you can see the black one here. This is the output, and the current if you divide the value of the voltage over the resistance. And you can calculate the same thing, the average, the average of this output voltage, and we can use the integration, the same method as we have seen it in the half-wave rectifier, and then we will arrive to this equation. If you compare between this equation and the previous one with half-wave rectifier, you will see here the value of this one is double. So for the diode, it will be V max over pi 1 plus cosine 0, which is you will get 2 V max over pi, right? The average when we have a diode. And then you can calculate the RMS using this equation with the same way. So to arrive to that one, you can use the equation and you can see the characteristics. You can also calculate the AC power of that rectifier using this equation. this is the summary if you would like to calculate the average voltage across the diode, or the average voltage across full wave rectifier as well, and the RMS voltages and also the powers. So you can use this equation for the calculation. For the three-phase, because of the, I don't have enough time to discuss that one, so if you would like, you can ask later on about that one. I'm happy to discuss that one with you. Now I will show you a video, and the video is implementing a full wave rectifier like this one here. Okay, if you look at this one, it consists of a transformer and then a 4 diode, which is four bridge like that one. So the first, if you look at this is the input source, it's 2 volt, right? And then step down the output here, which is target is to get 5 volt. Okay, 5 volt to charge mobile or something like that. Yes, DC. Exactly. So if you look into this one here, the target is to get 5 volt here to charge some mobile or something. This is the transformer to step down the voltage first, and then
In this tutorial, I'm going to cover silicon diodes, bridge rectifiers, and how you convert AC to DC. Here's the schematic symbol of a diode and a picture of the real thing. The little stripe on the end of the diode tells you which way to put it in your circuit. But what is a diode? A diode is a device that only allows current to flow in one direction. A helpful way of remembering this is to compare diodes to water valves that only allow water to flow one way. So if you feed an AC voltage or current through a diode, the negative voltage will just get blocked off, and you'll be left with only the positive half of the waveform. This process is called half-wave rectification, and it doesn't have to be with just a sine wave. It'll also work with square waves, triangle waves, or any other waveform that dips into the negatives. Wait a minute. If you zoom in and put the waveforms on top of each other, there's a voltage missing. Well, that's because there's no such thing as a perfect diode. All diodes will have what is called a forward voltage drop, or VF. This means that whenever current is flowing forwards through a diode, there will be a voltage drop of usually around 0.7 volts. The exact number will vary with temperature, current, and the type of diode, but for now let's just say it's 0.7. So a silicon diode won't even turn on until there's 0.7 volts across it, and after it's turned on, there will always be that 0.7 volt drop across the diode. Check out these examples to see what I mean. With a negative voltage on the input, the diode can't turn on, so you get nothing on the output. With 0.3 volts on the input, it's still not enough to turn on the diode, so again you get nothing. With 0.9 volts on the input, it's just enough to turn on the diode, but because of the voltage drop, you only have 0.2 volts left. And with 10 volts minus 0.7 volts, you get 9.3 volts. Now, sometimes that forward voltage is a problem, sometimes it's not. For the example I was showing you here with the 10 volts peak-to-peak on the input, it was almost unnoticeable. But if I was trying to rectify half a volt AC, like the signal coming out of my MP3 player, that 0.7 volt drop becomes really annoying and it doesn't really work. You'll have to use advanced techniques like superdiodes to deal with it, but you don't need to worry about that for now. Now, nothing is ever 100% efficient, so let's talk about power ratings. How can you predict whether a diode is going to melt on you? Well, the power wasted in a diode is given by VF times the current flowing through the diode. So for an ordinary silicon diode with a VF of 0.7 volts, with 1 milliamp flowing, only 0.7 milliwatts are being lost to heat, so who cares? But at 3 amps, you're generating 2.1 watts of heat, which is quite significant, so you'll either have to use a bigger diode or use a diode with a lower forward voltage like a Schottky diode, and I'll cover those in another video. Incidentally, no matter what anyone tells you, you cannot reliably put diodes in parallel for more current. What happens is one diode ends up doing all the work, and the others just end up heat-sinking the other diode. The last non-ideality that I want to talk about is diode switching speed. The 1N4007s I'm using here are designed for low-frequency power electronics, like the 50 to 60 Hz AC in your homes. Now, watch what happens when I increase the input frequency. After about 15 kHz, the diode becomes useless because it starts conducting backwards. This is because it takes a certain amount of time for the diode to switch between allowing current to move forwards to blocking any current trying to move backwards. Different diodes will have different switching speeds, so if I replace the 1N4007 with a 1N4148, things work nicely all the way up to 100 kHz and beyond. For radio frequency applications, you'll want diodes that switch even faster. So, whenever you're designing something, you'll have to think about your diode's maximum rated voltage, the forward voltage, the current rating, and the switching speed. Always Google the datasheet for the diode you're working with. Okay, that's most of the diode theory you will ever need to know, so let's use diodes to build something. The most common use of diodes is to convert AC to DC, to power the different gadgets that you have at home. I'm going to show you how to build simple unregulated DC power supplies, and one of them ends up being very similar to this one I have here. I'll start with a very simple low current supply, and then I'll show you how to improve on the design so that it can handle heavier loads. You start out by stepping mains voltages down to a lower, safer AC voltage. I showed you how to do that in my tutorial about transformers. With zero load, my transformer is giving me a nice clean sine wave of around 39 volts peak to peak at 60 Hz. Now, when I add in a 1N4007 diode and measure the voltage before and after the diode, you can see the negative voltage gets cut off. Technically, I have just converted AC to DC with just one diode, because I've eliminated all of the negative voltage. But this isn't very useful DC, is it? Half the time you've got a weird hump-shaped voltage, and half the time you've got nothing. So you're going to need a little more stability than that if you're going to power anything useful. So, we add a capacitor here to smooth things out. I'm starting with 1 microfarad, but the more capacitance the better, because you'll have a bigger energy reservoir. That's more like it. Now I have a perfect DC output of 18.7 volts. Whenever you're creating a DC supply, this is ideally what you want to see on the oscilloscope, a constant, stable voltage. Now, unfortunately, the only reason why things look perfect right now is because I haven't put any load on the supply yet. The capacitor got charged up through the diode, and right now there's nothing that would ever drain that capacitor. So, let's see what happens when I add a 4.7 kiloohm resistor as a load. Ohm's law predicts that this should only be a 4 milliamp load, which is very little, but take a look at what happens. What you're seeing here is that when the AC input is positive, the diode allows current to flow through, so the capacitor gets charged. But as soon as the input voltage starts dropping off, the diode blocks the backwards flow of current, and the only energy source left is that tiny 1 microfarad capacitor. And as you can see, it gets drained pretty quickly, even under low loads. So what do we do about this? Well, let's increase the size of our energy reservoir so that we've got enough to last us until the next time the input waveform goes positive again. Let's replace that puny 1 microfarad capacitor with a beefier 470 microfarad capacitor and see what happens. Hey, that worked really well. Now we have a DC power supply that will handle a few milliamps, which is enough to power some sensors and op-amps. Okay, let's turn it up a notch. With a 10 ohm load, this circuit should draw a lot more current. Well, that sucks. Now we're back to the situation where the voltage is sagging in every cycle. The average voltage is 8 volts, so we're only drawing about 0.8 amps, and the magnitude of the voltage ripple is just huge. Imagine trying to power something with this. The voltage would constantly drop so low, it would never even stay on. So even 470 microfarads is just not cutting it anymore as an energy reservoir. One thing we can do now is take the brute force approach and add even more capacitance. So let's see how the circuit performs with 3400 microfarads. Well, it's better. Now we're getting an average voltage of around 12.5 volts, so we're drawing an average of about 1.25 amps, but we've still got 5 volts of AC ripple, which is a lot. Now, we can keep adding capacitance all day long to reduce the amount of sagging between cycles, but for loads of several amps, it just becomes really impractical and expensive. So take a look at this cool trick. If you take 4 diodes and arrange them in this way, you form what is called a bridge rectifier. It works like this. In the first half of the sine wave, where the top wire is more positive than the bottom wire, these 2 diodes turn on and allow current to flow forward. The other diodes stay off, blocking any possible reverse flow of the current. Now in the second half of the sine wave, where the top wire is negative with respect to the bottom wire, the other two diodes start conducting, and the other two turn off. So instead of wasting the bottom half of the AC waveform by clipping it and never using it, you just reroute it and flip it around. So on the output, you get DC at 120 Hz instead of 60 Hz. And just like before, you can filter it with capacitors later on to get a nice smooth voltage. You can buy pre-made bridge rectifiers, but it's also easy to build them yourself. Here's mine connected to my transformer. I made it out of 4 1N4007 diodes, and it cost me about 4 cents. Take a look at how the voltage used to go from positive to negative at 60 Hz, and now it never drops below 0 volts, and instead we get these positive constant voltage bumps at 120 Hz. This is called full wave rectification because we're rectifying the full AC wave. Now, let's go back to our breadboard with a 10 ohm load and see how the bridge rectifier performs with 470 microfarads of capacitance compared to the single diode solution that we made earlier. Now we get an average of 11.6 volts instead of the 8 volts we were getting earlier with a single diode. And you can see that's because the bridge rectifier is charging up the capacitor twice as often because we're using both halves of the 60 Hz mains AC cycle. Now think about how much difference that made, given that those extra diodes only cost me 3 cents. Bridge rectifiers might be a little harder to understand, but since they work so well, everybody uses them. Now let's compare the single diode with 3400 microfarads to the bridge rectifier with 3400 microfarads. Now we're getting an average of 13.5 volts instead of 12.5 volts, and we only have about 1 or 2 volts of ripple. In other words, the combination of a bridge rectifier with high amounts of capacitance can turn almost any high current AC supply into a useful high current DC supply. Just keep in mind that your diodes and capacitors have to be rated for the voltages you're working with. So what we've got here right now is basically the same thing as what's inside those cheap little unregulated AC to DC power supplies that are used to power radios, clocks, and other gadgets around the house. You could make a 9-volt version and it could power an old Sega Genesis or Super Nintendo. The final thing that I want to highlight is that these are all unregulated DC power supplies. That means that even though we've successfully smoothed out a lot of the voltage ripple, we'll still have the problem of the average voltage changing under load. With no load, it's 18.7 volts out, and for loads of around 1 amp, you get about 13 volts out. Now, for some circuits that won't matter if they're designed to work with a wide voltage range, but for things like microcontrollers and other digital electronics, they'll want a voltage source that is very precise, and for that you'll need to create what's called a regulated voltage supply, and I'll cover voltage regulators in another video. In the meantime, now you know what diodes do and how to convert AC to DC.